Okay, so I will make a start. It's 9:30. Okay. So this week, mentioned it a couple of times, we're going to be doing layout predominantly. So by this stage, we've sort of got our schematic to the point that it's, you know, we can start laying out and our components are all ready and placed on the schematic. So criteria, we're going to do a bit of a follow-up on a question that you raised last week, Doomy, about the input filter. I've had a couple of questions on other elements as well, coming from a couple of different people, so go over that. And then, like I say, we're just going to go straight into the layout, and I'm going to do like a bit of a demo on Proteus of how to get going with the layout, what the first things you need to do. But a lot of it really is going to be just having a go, because you have to just kind of have a go at this to understand how to untangle nets and that kind of thing. So corrections initially. So I've just renamed this project to a dual class headphone amplifier, and I've changed the revision to 0. Revision to 0 because it's version 1.0 rather than 1.1. It just didn't really make sense. And dual class is obviously class A and class AB, because we can switch between the modes with this design. So another query that's come up a couple of times is, how do you know what to put in these boxes? So you're doing the properties and you've got voltage, like what goes in voltage, you know what I mean? So the answer to that is you use the most pertinent value for that specific component. So for example, if we take a Zener diode, the most pertinent voltage of a Zener diode is, what's the most pertinent voltage of a Zener diode? Breakdown, exactly, because you use the Zener in its reverse breakdown voltage all the time. What about a rectifier diode? What would be the most pertinent voltage of a rectifier?
I would say the forward conducting voltage.
It's either that or
Breakdown.
the reverse breakdown, yeah. So that would be, you know, essentially it's the same. So it is the same voltage parameter. But obviously in your Zener diode, you're constantly using it in the reverse breakdown, whereas in a rectifier, you never really want to exceed that voltage, because you know that's what it's there rectifying. So linear regs and switch mode power supplies, you'd use the output voltage. So you can have a 5-volt reg, a 12-volt reg, that kind of thing. So max current draw and max power dissipation. That's kind of self-explanatory. You'll always use those values when you're specing these components. And then there's a special box as well. That's for you to put stuff in there. So if you want to record the forward voltage drop of a Schottky or something, then you can stick it in there as well. Or a good one actually is LEDs, like green, blue, red LEDs. They've got varying forward voltages that you need to overcome before you can even turn the thing on. So that'd be useful to put in there. Right, so input filter. So there was a question last week as to whether we would get a filter when we build this circuit with C1 and R2. Because this op-amp, can anyone tell me the two ideal rules of an op-amp? What are the two main rules of an op-amp?
Infinite input impedance.
Yeah.
And zero offset between the inputs.
Yes, it'll do its best to maintain the voltage between the two inputs, given the right circumstances, yeah. What that does, if you're maintaining the same voltage at the two inputs, the question is does that mean that you've essentially created filters between the two input legs? Now, if this was the case, then we'd have, that's our DC blocking cap, because we don't want DC to get to our headphones, otherwise you'll break them. And then this is potentially the filter that could filter to ground, creating a high-pass filter. This filter would be 482.29 hertz. Now, to give you an idea of what that would sound like, that's 482 hertz. That means that that's the frequency that it would start filtering at, and then everything down here, all of that would be attenuated. That would sound awful. So it would just be completely not usable as an audio amplifier. So is that what we get? So good thing is we can simulate. I use simulations all the time, as you probably guessed by now. Green is the voltage input, brown is the voltage output. There's something terribly wrong with this the simulation as it was depicted. So what's happened is the output has hit a rail against minus 10 volts. That would absolutely not work. So the reason for that is because this input pin had no reference to ground. There's no bias. So in reality, even though one of the two rules of an op-amp is that it takes no input current whatsoever, that actually isn't true. There's always, nothing's perfect. So as this pin is drawing a fraction of a little bit of current, that will create an offset with that capacitor. So I've added a 1 meg resistor here to give that reference, and it's obviously, centered it around 0 volts again. We've got potentially two filters, one created by these two components and one created by these two components. One is 482 millihertz, so half a hertz, and one is 482 hertz. So if we actually run a transient analysis, so this is a Bode plot, frequency in, and you measure the frequency response of a device or a circuit, we can see that at the minus 3 dB level, which is what's specified as the corner frequency of a filter, is 478.93 millihertz. So it is in fact that we haven't created that filter across the legs. Can anyone hazard a guess why we haven't created that filter across the legs? I know you know, Dimi, already, because we've...
Yes,
Does anyone have
There's no path for that current to go.
Yeah.
Basically.
Because even though the voltages are held the same, there's no way for the current to share. So there's nowhere for that current out of the capacitor to dump into the resistor on the other side.
Put that 1 meg in there.
No, it's nothing to do with 1 meg. The only reason why you can kind of ignore that 1 meg, there's no, because this capacitor can share current with that 1 meg resistor. It can't share current with that 1K because there's no current in and out of these points. Even though the op-amp holds these points at the same voltage.
Except it's negligible if there's any.
There's a, yeah. When I say no, I mean, it's
Gotcha.
very, very small. So that's confirmed that we've only got the filter of these two components, and I needed to add that because, because of the bias. Okay, so compromise. I put a 1 meg resistor there, but I've actually specified it 22K. The reason is that if you didn't know, the higher the resistance value of a resistor, the more noise it generates. High resistance resistors are noisy. They get noisier. And the reason for that is this thermal noise equation. E is the VRMS of the noise. And then you've got a bunch of terms multiplied together. You've got bandwidth, we can ignore because that's constant in our case. T is temperature, R is resistance. So as you increase R, you get more thermal noise. So what I've done is I've specified 22K for less noise, but then I've had to increase that capacitance slightly to make sure that our frequency response is still good, 7.17 hertz. So that'll be absolutely fine. Right, let's get to it. So that's just a bit of a background on where we are with the circuit and that kind of thing. Right, so I've got a big list of stuff here, and what I'm actually going to do is I'm going to look at this list and I'm going to show you how to do it on Proteus, because this, if this is the first time you've seen it or you want to set it up properly, this is how you do it. So what I'm going to do is start. See that? Yeah, cool.
Just ask a question. Originally, you'd had NE 5532 APs. Seems you've changed it to DR. I missed that. Why did you change it?
Did I? I can't remember.
Does it matter, basically?
I think, is it the APs in a PDIP package? I think the AP's the through-hole larger device.
So you went to a Surface Mount?
I went to a Surface Mount one.
Oh, okay, so we changed that as well.
I don't even remember that I did that. If I did, I should have.
We changed the regulators.
Yes.
We need to change those as well.
Yes.
Okay.
Oh right, yeah. I mean, if I haven't, yeah, definitely. So this is the. If I show you, well, I'll be showing you the proper thing, but that's the SOIC package there.
Fair enough. Okay.
Yeah, apologies if I didn't go through that. So, cool. So we're at this stage now. So we've got our schematic ready and all our parts are okay. So the first thing that we want to do is open the PCB layout tab, which is that little microchip looking thing. And we're going to have like a completely blank board. the first thing is to set some keyboard shortcuts. So system, set keyboard mapping, and you have to do it separately from the schematic capture side. So the first thing that I want you to do is set cut, copy and paste, because you always need that, and I don't know why that they don't assign it. Copy, paste, and then we want to scroll down all the way to this mode selection commands, and then I want to set these. So S for selection, C for component, P for package. Can you guess where this is going? See, we're not going to use differential mode pair that much, so I'm not going to set it. V for via, Z for zone. That just makes this process a lot easier when you can just tap the keyboard and jump to the tools. Those tools, by the way, are all these up here. All these tools that we just set are up here, and you'll use that all the time. So the first thing I'm going to do is create a board outline, and so this little menu down here is selecting all the layers that we've got on our board currently. And our board outline, there's actually a specific option for it. So click it, and then these are your sort of like drawing tools. So you can draw lines and arcs. You can put text on the board. I'm going to draw a square. There's two ways to do this. You can either, bear in mind as well, I'm in the metric grid. So this bottom right, millimeters. If I press M on the board, it changes it to thou, imperial, metric. I'm also going to press F4 to make sure that I'm in the largest grid snap. So this is a really coarse grid. Two ways to do this. One, can you see at the bottom where it says width and height? Is that, yeah? So we're going to make boards that are 70 by 70. So you can either do this and then do it that way. Obviously I've put that on the silk screen layer. So what I need to do is select it, right click, and you can change layer. So if you put something on the wrong layer, you can just change the layer like that. Board edge. Or there's maybe a better way to do it, to delete that. And then we're going to place any old, it keeps going on silk. The reason why that is because when I click this square, it jumps to silk screen, so you have to click the square first and then go to board edge, and it'll just do it now. So I've got a randomly sized one, pressing S for select tool, right click, properties, and then I'm going to change the width and the height here. 70 millimeters, like so. It's a bit more accurate, a bit quicker. The other thing that you can do is double click it and center it around the origin. So if you press 0 and 0 of these coordinates, can you see it's centered around the actual origin of this board? I've got a few components at the top there, but I'll talk about those later. So that's our board edge. So that's the first thing essentially you want to do. By the way, when you're doing boards and there's no specified mechanical thing that they're fitting in, you can start with a board edge, but then change it, because you might find that you can get it a bit smaller, a bit bigger. It's what I did when I did my layout for this board. But I found that this is probably big enough. Right, so the next is the layer stack up. So I think, yeah, technology, set layer stack up. Now on here, we've currently got 2 layer boards. We're going to create a 4 layer board. And the way that we do that is you click stack up wizard and we set 4 layers. I'm going to keep these parameters constant for now. Now we've got 4 layers on our board, but what we actually want to do is make sure that this board, the board information, lines up with the manufacturers who's going to make your PCB, because you can set copper thicknesses, and you can set dielectric constants for the FR4 material. So I've already done this, so I'm not going to go through and change all of these things, but in the presentation, which I'll show you, this box here, that contains information that you'll need to put into your design. Okay, so it's just a matter of looking at these numbers and putting them where they need to be. I've picked that information up from JLC PCB, and those are the guys who's going to make our boards for us. So you have to set your stack up against theirs. Power planes. So we've got 4 layers. We're going to use 4 power planes. you click the layer. Well, actually, you don't need to click layers. You just click create power plane at the bottom, and then we set this, the planes up at this point. So on top copper, I'm going to set plus 12 volts. On inner 1, I'm going to go ground. On inner 2, I'm going to go ground. On bottom copper, I'm going to go minus 12 volts. Plus, ground, ground, minus. If we look at the board view and look what that actually looks like, we've got plus and ground are very close to each other, physically, on the board. The two ground layers are miles away from each other. Like, that's just the way that this goes, you know what I mean? When you make a 4-layer board, you've got 2 layers that are well close to each other, a big gap, and another 2 layers that are really close to each other. If you create these 2 layers that are close to each other as plus and minus, well, some plus and minus, ground and another plane, you create a capacitor. That's a good thing, especially for EMC purposes. The reasons why is complicated, so I'm not going to go into it, but essentially you create a very, very low inductance, fast capacitor. So when a device wants to draw a lot of current all at once, you've got those layers. So that's why we're doing that. Like I say, it's good for EMC, and it's good for noise. Cool. Next things, we're just going to quickly set the tracks that we're going to use. So we're going to mainly track our board in T25. Okay, so you click the track button, or you press T, because we just set the shortcut, and click T25. And then we're going to set our vias. So click the via, and then set to V30. So what does this look like? That's a V30 via, and the track, that's a T20, is it? Just double check that. Track T25, yeah. That track looks quite thin to me. Default, right, okay. What I haven't shown you is technology. This is what we want to do. We don't want auto tray style selection. That's what was doing that. And we don't want auto track necking either. So get rid of those. Now we can set our tracks and it'll stay there. So set that. Set that. So this should actually be a bit bigger now. Place the via. Place the track. Oh, come on. T25. Yeah, there you go. Right, so we're getting there. We're close to having this board set up, ready to go. In fact, I think we are. So what do we do next? You've got all these components and you've got a blank PCB. Where do you even start? The first thing that you need to do is place all of the big chunky stuff, but more importantly, the mechanical stuff that can't move. So you're going to have mounting holes, I assume. With a headphone amplifier, you've got a volume potentiometer, or you've got a DC jack. Those things have to go around the edge somewhere. So place all the stuff that's fixed. So that's what I'm going to do. So what I've done is I've already put these components out ready for this demo, basically. But the way to add and remove components onto the schematic is you go into here, component mode, and then you've got all these components. All these components are from the schematic. So if I place this green LED, it disappears off the list off the left. But if I delete the LED off the board, it appears back in the list. So you know that when that entire list is placed on the board, you haven't got any more components to go on. So what I'm going to do is I'm going to rough out where I think some of these bits can go. In fact, the first thing I'm going to do is I'm going to place some mounting holes. So how do you do mounting holes? So through hole pad, I've created one called M3 already. To create these pads, you just click the C for create once you're in this area, and then you can call it, M3, M4, whatever, and then you set the sizes. So if I go back to here and show you what's the sizes this are. So I've got a diameter of 4.5 millimeters, which is that annulus, so it's the copper bit, but then I've got a hole of 3.2 mil. 0.2 mil is a bit of clearance for an M3 bolt. You just need a little bit of, you can't make it bang on. So what that is, it's a pad with no net associated with it. So what I'm going to do is I'm going to change my, you see I've changed the thing, the pitch of the grid. Just move it away from the corner slightly. And if I right click it and then change it to the mounting hole layer, the pad part of it disappears and it just turns into a mechanical hole that you can mount stuff to.
Is there a quick way of changing the pitch? Is it just F4?
Yeah, so F2, 3, 4,
Okay.
and also I think it's Control F1 by default is your finest pitch. So that's Control F1, F2, F3, F4.
And
That you
is
use.
F4 default?
F4's default. Don't know.
Okay.
I flick through them so often.
Yeah,
When you're doing boards, you'll fly through that stuff all the time. So you'll need to know that Control F1, 2, 3, and 4 is these pitches. So I'm on the F3 pitch now, metric. So then you can just copy paste it, and then you just want to make sure that you're putting it in the exact same position. That's not. And you can measure this stuff, and I would recommend you measure it as well. One of the easiest ways to measure it, I don't know whether you're meant to do it or not, but this is what I do. You click the line mode here, and if you click on the center of a pin or something, and you just hover it over to the other side, at the bottom it says length 62. It's a dead quick way to measure distances. So I'm going to select these two, copy them, and then paste them down here. Now obviously I've not done that right. Put that there. Okay, so we've got some mounting holes, good. Now, there's not much other mechanical stuff that's going on this board, so I'm going to start moving these components over. These two, can anyone guess what they are?
Regulators.
Yeah, yeah. And I've got these two things. Any guess what these are? DC jack. That's the DC jack, yeah. And that's the battery terminals that we can use to solder a 9-volt battery onto. By the way, if you do something wrong, like you try and put a pad within a pad, you get this thing called, those two pads are connected together, so there you go. You get a DRC error. You don't have to display that every time, but it just highlights that you've made a terrible mistake and your circuit's going to set on fire. So we've got these left. This thing here.
The potentiometer.
Yes, exactly. Now, can you see that there's a really faint outline there? That's like your keep out zone. That's telling you that the potentiometer knob is like going over to the left. If you don't know the orientation, like how do you know that it's not this way? You know what I mean? You need to then check the data sheet and make sure you're placing your components in the correct orientation, because, not good otherwise. And then, I'm just going to move all these down here a bit because this is... So the first thing I'm going to, not first, the thing I'm going to show now is layers. So obviously you've got all your layers at the bottom here to select them, but you can actually turn them on and off. And this is one of the most important things that you'll ever learn to do. So you can click this button here, or you can press Control L, and this brings up all the layers. If you click none, you don't see anything, and then you can selectively choose which layers that you want to view at any given time. So I'm going to view everything, but I'm going to get rid of those force vectors. And I'm also going to get rid of the force vectors. Just show you where that component wants to be based on the connections that it's got. It's like a movement. It wants to be closer to the components where it's got most connections, and that's what the force vector tells you. I don't really use them that often, to be honest with you. The rat's nest is obviously the connections to the pins. So I'm going to turn the rat's nest off, because it just, when you're doing this, this kind of thing, it gets a bit confusing. Adds complexity to the board that doesn't need to be there. So we're kind of roughing in. It's very rough, but we're kind of getting an idea of where these components might be able to fit. And these two are our audio jacks. So that's I've called one J in and I've called one J out, just so that when you're looking at the silk screen, it's easy to tell what's what. Right. So now we've got our mechanical stuff on there. What do we do next? So this is when we start adding components and building up, let's say, a channel. So the first thing I'm going to do is I'm going to build up this channel. You could finish off the power side as well, which is, you know, equally as important to do. So I'm just doing this one of the channels just as kind of a demo here. I'm going to demo a channel, and then that's going to be it. I'm not going to lay this whole board out because we'd be here all day, and that's just this won't be doable. So where do we begin? What's the first thing that you would place next to that op amp? What would be kind of like the most important thing to do in terms of placing components? Which capacity? Yeah, both are important.
Yeah, the DC blocking.
Not quite.
Coupling class.
Yeah.
Of course.
Yeah. So your decoupling caps want to be as close to the pins as possible on your devices. So C6 and C7. And I'm just going to rough that in now. So going over here, C6 and C7. I'm going to turn the rat's nest back on. There's one little trick that you can do. Oh, plus and minus on the number pad flips your components around. There's one little trick that you can do that will start to untangle the rat's nest a little bit. You see these two components both go to ground. We've got two inner ground layers. Every single time that you want to connect something to the ground, you don't have to do this, but I'd recommend on this design, put a wire straight next to it, and you can ping it straight to the ground, the ground planes, internal ground planes. So the way that you do that is press T for tracking. Pin 1 here at the bottom. Can you see just here? It says the net is ground. So I know that pin 1 is ground. I'm going to click to start making a trace, and then I'm going to double click to place a wire. Now I'm on the bottom layer, and I've got this sort of trace that's following me. If I right click to get rid of that, it just stops there. And what we can see is that wire, just as a quick demo now, has connected not to the top layer, no connection, not to the bottom layer. It has connected to inner 1 because it's literally touching, and it has connected to inner 2. So that's showing that you're essentially the wire will automatically connect to those layers. Now if I do the same on this chip, I meant capacitor, the rat's nest between them disappears entirely. So that's how you can kind of start to sort of immediately get rid of a bit of rat's nest on the board.
So that's shown by the colours. Is it like the black is joined to the yellow, or the layer? So the layers, is the layer coloured yellow or something? Or
This,
the layer, because that's on the first layer down, isn't it?
it's on all the layers, yeah. So this wire is actually on all the layers. So if I show you layer by layer,
But it's connected to the second layer down, or something.
and the third.
And the third.
Yes.
Oh, both. Okay.
So if I look at top layer only, you can see this big void, this big gap around it.
Oh, okay. Yeah,
That's not
right.
connected at all.
Right, yeah.
Bottom layer isn't.
Isn't connected.
Inner 1 is, because it's just butt up against the
Ah,
thing.
Yes. Okay.
And inner 2 is.
Is right. Got you.
Yeah. Cool. The other thing, right, is a lot of surface mount components and devices are actually built in the imperial system, not the metric system. So you might want to place them in the imperial system as well to keep things neat and tidy. So one way that you can do that is, another kind of tip is false origins. So if I'm going to press O, I can press O on a, I don't even need to have it highlighted. So wherever my mouse is, if I'm hovering over a pin and I press O, you can't really see it very well, but if I turn all the layers off, I've placed a false origin, and that is instead of, so that's the origin of the board right in the middle, but the false origin is just down off the bottom. Or in fact that's the other way around actually. That's the real origin, the false is under here. The grid, what I'm trying to say is the grid aligns to that origin perfectly. And if I press M now, we're in an imperial grid. So you can see 1, 2, 3, and 4. This grid now perfectly aligns to these pins. I'm also going to snap down to a slightly tighter grid. to place this component slightly closer. Always make sure your reference designators are not getting overrun by stuff. This is another slightly confusing concept. Our top layer is plus 12 volts. This decoupling cap is plus 12 volts, that pin's plus 12 volts. So you've actually already got a connection between those 2 points. Does that make sense? What I tend to do though is put a thicker track, because you've only got these thermal relief tracks going there, so put a thicker track. And you see this track overhangs slightly at the bottom of here, so I'm going to make this track slightly smaller, the T20, so it's not overhanging the pad. Right. So, as you said before, Parik, feedback path is really important. The feedback path of here is output through J3, R1 back in, and R3, we can place R3 close as well. So R1 and R3, I'm going to place them on the board. R1, R3. I'm going to change the grid snap to a bit slightly coarser, because we might not need such a fine snap. Move that out of the way. Move that sort of closer. Bear in mind, this is another one of those mechanical things. You need to get fingers. Your fingers are going to have to get in there to put jumpers on and off these pin headers. So be careful how close you put it to other stuff. So how do we sort of approach this? We want to see what pins connect to what, and we want to try and untangle the net as best as we possibly can. We don't even really need to start placing stuff yet. If I grab hold of this component, it's a bit confusing to see, but can you see the 2 green lines cross each other? If you flip that component round, the green lines aren't crossing each other anymore. On here, we can see this pin, pin 1, is connected to that via. It wants to go there, so that's a ground pin. So you could even place a ground via now to show you that it's not going to, you don't need to track it out. So what I'm doing currently is making this a little bit neater. I've got these 2 on top of each other, so just move them out of the way. So now, let's just check if that works. We've got a route here. I'm going to change the trace to T20 just for this pin connection here. You've got a route into here, which is neat still. You've got a route down here, which is neat. Oh, when you've got that invisible sort of highlighting thing there, you can just press enter, and it'll just do the trace for you, if you want to take that trace. And then that is via, change the trace back to T25, larger, place it down. So you can get a feel that you can kind of untangle this stuff before you even place tracks down. That's really, really important. You want to untangle the nets as best as you possibly can before you start tracking. Right, so all I'm going to do is essentially finish off this one side so you get a feel for it, and then I'm going to show you the finished product, the one that I did, and talk about a few features of what I've done. So we've got C1 and R10, and that's incoming from this potentiometer. So those don't actually have to be very close to the op-amp if you don't want it to be. You've got C1, R10. I've put a few tracks down here just as a demonstration, but really the way that I do this is I'll track things that I know aren't going to move or are barely going to move. So you'll track the things, keep the things, like, what I mean by move is these components are going to be very close to that chip, and if I track them now, I'm happy to leave the tracks there. You don't want to track the tracks that go all the way across the board, because they're likely to move and change as you do the design. So you can put traces down which are, in tight chunks that you can then move around, but don't get into the habit of putting traces down immediately. It's important to place your components and get an idea for where they're going.
Is this the very top layer?
We're on top layer at the moment.
The top layer, and you were saying about the 0 volts and the power rails of that op-amp.
Yeah.
Were directly joined, and you still put this track in between it.
These two.
It's a nice thicker track.
Yes.
Or whatever. How are they joined without that track? Because surely everything on that layer isn't joined together, is it?
No, but can you see this connection here, this thermal relief connection to pin 8,
Right.
and pin 7 doesn't have any of that. Pin 6 doesn't either. So any pin that's on the 12 volt connection, that's got a 12 volt power connection, is going to automatically connect.
Oh, I see. Yeah.
I haven't done that. Proteus
It's
is
already because of the schematic.
yeah.
Yeah. Okay. Gotcha.
So I'm putting a track there only to increase the
Right.
thickness slightly, to lower the inductance slightly
Right. Okay.
between those 2
It's good
points.
practice.
It's yeah. I mean,
Especially as it's compensating or a decoupling capacitor.
exactly. That's the point. Exactly. It's probably a bit of a non-standard thing to do that particular thing here, but that's my preference. I prefer to just get a good low impedance connection
Yeah.
at that point. Cool. So we've got these components over here. Again, you're doing a similar sort of thing. We know our C1 is our DC blocking cap, so that'll definitely carry signal through. R10 goes to ground. One side of it goes to ground. So you'd usually do this on 2 screens, so you can look at your schematic and your layout at exactly the same time. But if I find the one that goes to ground, it's not that, and just put a via there, then I know that I'm only concerned with these. So if I flip that upside down, stick it on top here, move the reference designators out of the way. C1's reference designator. So now, again, I've untangled it. Can you see that? It's untangled. This is the one I wouldn't recommend putting that track in. You could, the track's done, but the chances are, as you start to build the circuit, you're going to have to put stuff across here, and components might need to go there, blah blah blah. So just do the ones that are close, and then that's going to make your life easier. And then the last section that we're going to do is this little bit over here. So R4, R5, D3, D4. R4, R5.
And notice the D1 disappeared. That doesn't matter, does it?
D1 disappeared.
As in, the first diode you made back a couple of weeks ago, we called it D1.
Oh right, yes.
Does it matter that there's no D1 in that now?
No, it doesn't. That's a good point.
It's still going to work, obviously, but
yeah, this is something that Taylor was sort of talking about before, about renaming your reference designators. There is a tool somewhere. I haven't done it for a while. I'll find out for next week. There's a tool somewhere where you can rename the entire sheet's reference designators all at once.
oh, that's handy.
And you can do it by sheet, and you can start with increments, so you can start with 1-0 for all the sheet 1 components, 2-0 for the next one. It's definitely worth doing that, and that's a good point. So I'll do that next week. But in terms of the schematic, it doesn't care what you call it. Yeah.
This is just a neatness.
Yeah, exactly. Q3 and Q1 are the last 2 bits of this puzzle. I'm just going to move these things out of the way slightly. Just try and detangle. And now I can move this thing as an entire block around. And I want Q3. Is it Q3 and Q1? Yeah. And Q1. So this is another sort of section. Now, because I've done this a few times, I already know what sort of works. So I don't need to sort of faff around. But this is a part of the process that you'll spend a lot of time doing. It's important to just take your time with this part and really, get to grips with what where the nets are and like I say, detangle. Just detangle the thing as much as you possibly can. We don't have to worry about high current traces or high speed traces and that kind of thing on this design, which is fortunate, which is why I actually chose something a bit simpler. So D3 and D4 connect together at a node here. So you can see that there's a trace between the cathode of D3 and the anode of D4. So I'm going to flip one of these around. And then, this is another point as well. Wherever you pick a component up, that's where it's going to snap to the grid. So can you see this one's not quite snapped to the grid? If I pick it up by this pin, it snaps to the grid on that pin, so you can correct for grid errors and stuff, snapping errors like that. Let's get rid of that.
How do you quickly flip it? Is it
Yeah, the plus and minus arrows
okay.
flip your component. Oh god. Just around like that. So I'm just going to get these reference designators. When I first started doing boards, my reference designators were like here. And obviously that's a hole. You can't print into a hole. I used to be terrible for them. So I'm really strict with them now. Because you'd get a board and you'd be like, oh god, I don't know where that goes. So I'm going to connect these two together. And then the other kind of trick that you can do is if you click a pin, you can see it. Proteus highlights where it wants to go, so you can kind of get an idea for where that track wants to be, which could help you in choosing locations for these components. That's a power track, so I'm just going to double click it so that it gets rid of the net so it doesn't confuse me. This one is a power again, so I'm going to do the same. That's already connected, which is nice. This is the little trick that I was saying before. I already know, I've done this a couple of times, so I know that if I put these two in this orientation, that lines up nice and neatly there. And then I've got these resistors, so that resistor is obviously a ground resistor there. Could potentially move these guys out of the way. Move this over here slightly maybe. Maybe fit this in here. Again, I'm just sort of playing with it at the moment. I don't know exactly where to put these components, is what I'm saying. So when you come to do it, you'll be playing with it as well. Maybe something like that would work. Let's do a quick tester. This trace is a bit too thin, or it's not too thin, it would be absolutely fine, but we're doing everything in T25, so place that. Place that. Place that. Okay, so it's actually kind of neat. So you can see now we can start to build up these sections, and to connect this lot to the rest of the circuitry, so you'd essentially be going through here. And then again, these jumps here are slightly larger. So again, I'd refrain from doing these big sort of jumps until you're happy with where this little module, let's call it, or this little collection of components wants to be. Because what you'd do is you can keep that as it is. It's nice and neat and a little compact sort of cluster. And then you can do the other channel. It's got two channels. So just do the two channels and then you can slowly work through it like that. Are there any questions before I jump on and show you the finished article? Is it clear enough? I've just burnt through tons of information. I'm going to put this on a video so you'll be able to come back and go through it again.
Are those regulated valves?
These?
Yeah.
Yeah.
And the number 2 pins are connected to ground, right?
Yeah.
Alright, so you can just put a wire on them.
You mean these two pins?
Yeah.
Well, one's a positive regulator and one's a negative regulator. Right. So, in reality, if I hover my mouse over...
The negative one, the 2 is positive.
Yeah, well you can see pin 3 is already connected itself. So pin 3 here is minus 12. So that's minus 12. That's plus 12. Pin 1 is ground, there. Pin 1 here is plus 15. So pin 2 here is minus 15, and pin 2 here is ground. So it's because one's positive and one's negative, a couple of the pins are switched over.
Oh, okay.
So it's just, but to connect, let's say you want to connect this pad to ground, there are a number of ways to do this. I suggest that we only put a couple of vias in. So I've started a trace in the middle. I'm going to double click to place a via, and I'm going to start another trace. I'm going to double click to place a via. That's connected the pad right in the middle of it to ground, on both the ground layers.
Yeah.
What you can another option is to thermally relief this, is you put many of these on there. This is not the way that you do it, by the way, I'm just showing. That would be a solidly thermal and electrical connection to the two internal planes. If you put in any power dissipation through that device, it'll spread the heat out and the whole PCB acts like a heat sink. That effect has a huge impact on the power capability of a device. It acts as a really good heat sink when you do that. So something to bear in mind. We don't need to do that because we're only going to draw if you're drawing 100 milliamps, you're going to hurt your ears. So right. So what I'm going to do is jump over to one that I made earlier. Same schematic. I've done it on a slightly smaller footprint. So when you look at it, it looks a bit confusing, doesn't it? Because you've got text on top layer, bottom layer. There's just stuff flying about all over the place on this. So the first difference really, I'm just going to quickly show the 3D view. The first difference is, once this loads, I've put components on the bottom layer and I've put components on the top layer, just for this particular one. I wouldn't suggest to do this because it makes, unless you want to have a go, it's up to you. If you want to have a go, have a go. It's fine. It just makes it a bit more confusing when you're actually tracking because of this. You've got like these two, I've put the two linear regs on the bottom layer, but then you can place components over the top of those components so long as you haven't got any through holes that are going to interfere with them. So what I was saying before about choosing your layers, this is why it's important. When you've got a board that's slightly more dense, there's your top layer. You can just use that on its own. It's unconfused the entire situation. You can even put your top silk back on and you can see where all the components are and what places to avoid. You can't see where the components on the bottom are. So if I put the bottom layer on now you've got a rough idea of what can interfere with what, but like I say, you can imagine it sort of gets a little bit confusing. But it's manageable. Once you get an idea of this, placing components on top and bottom, it's manageable. Other things to note, I've added some text to tell you where to put the jumpers to set up the device. So jumpers one, put a jumper between pin 1 and 2, it's normal. 2 and 3, it's compensated, and that takes the feedback of the amplifier from here and puts it to the output over there. And again, you've got these other pin headers here. So put it on jumpers on pin 1, 2 and 3 and 4, it's in class B. You get rid of all the headers, you get rid of all the jumpers, it's in class A. Class AB. I put silk screen of my name and that kind of thing as well. Other things that you might want to do. So you see this pin here, I've necked down the track slightly. So I've got a thick track all the way up to it and I've necked it down just a little bit to meet the pad properly. The way to do that is place the thicker trace, and then you can right click anywhere on the trace, go to trim manually and right or left click somewhere else on the trace, it doesn't matter where. Change the grid snap to something finer if you want a slightly better pitch. If I click this, now I've got this little section of track, I can right click it and then I can change the size. So that's how you can neck down traces if you need to connect like that. Other things, so I've told you about the vias that you can put in the pads, just in this case here. We've got that connected around. Right, okay. That is essentially, I think that's all I'm going to go into detail on this particular part. On the other board, you've got a lot more space. So you can keep all the components on the top side. It'll make the whole process a lot easier. Cool, right. So I'm going to jump back into here. So we've done all that. So just to quickly recap some basic rules. You do your outline and mech first. Place the components in sections as it occurs on the PCB. On the schematic. Symmetry is beauty. So try to keep things symmetrical. Don't, you know, if you've got little traces, you know, that are slightly offset, or your trace widths are a little bit incoherent, just try and make it as neat as possible. Power decoupling cap pin. I didn't describe that. Whenever you're doing a decoupling, let's take that capacitor. Okay, so this decoupling cap's on the bottom where it doesn't really matter. Power comes in. Oh no, that's on the plane. Is there a better one to choose? Because I put this on the bottom layer and this other one on the top layer, it'll be easier if you imagine this power plane isn't there. So if for example, let's choose one of these, turn top copper on. I'm just going to get rid of this power plane for now. Power comes into the decoupling cap. It goes, sorry, that's ground. Power comes in from the nets. So what would actually happen is you would have power coming in to the decoupling cap. Okay. Trace. Power would be coming into the decoupling cap at that point. Oh, God. This is why this is that auto trace style selection. It's not very useful. Oh my God. Never mind. So you're coming in through that input power. It goes through the cap and then it goes into the pin. That's the point I'm trying to make. You want to, the point of the decoupling cap is to decouple the inductance between the incoming power trace and the chip, so before and after. So you always want to, because you could place power directly into the pin from here, for example, and that wouldn't be the best type of decoupling. So that's what you want to do.
You want to go to the pin of the cap first.
Pin of the cap and then to the pin itself through a short low inductance trace. Every ground and power pad gets a via. You don't have to stick with that rule for every design that you ever do, just this particular one. It allows us to connect our planes together very well at the points it needs to be connected. Keep the feedback loops short in op amps, because otherwise you might cause oscillation. If you've got stray capacitances, inductances, it's important to keep those loops short. Thicker tracks is less resistance, less inductance and more capacitance. The capacitance can be mitigated. So by and large, thicker tracks, especially for power delivery. So if you're doing power delivery tracks and you haven't got planes to work with, thick traces, always remember. Be mindful of the mechanical stuff, usability. I put fat fingers. If you've got fingers and you're trying to do a potentiometer and you put it next to a DC jack. Verify the integrity of your ground planes. There's a slide for that. Silkscreen version, I showed that, and check all the reference designators so they're not all on top of each other.
What's the drawback of using more narrow tracks for the power?
Predominantly, there's two issues. DC resistance goes up,
right,
because you've got less copper, so it acts more like as a dissipative DC resistor. But also your inductance goes up, which is more of a problem, really.
More of a problem than the capacitance model.
Yes, for the trace, yeah. It's for power traces, an increased capacitance is actually a good thing, because then it can deliver. It itself is a capacitor, a decoupling cap in a sense.
Right.
Increased inductance is bad, because that's the thing that will restrict current flow when an IC, for example, switches from a 0 to a 1. And you've got that, that digital level shift.
Yes.
It requires current to do that, and especially the quicker it is, the more current it needs. That's why you want thicker traces. Power plane check-in. Once you've got all your components on the board, and you think you're good, you might not be good, even though Proteus says that you are. So on here, we've got our top layer as plus 12 volts. And let's see where that's actually, because this is what I actually did. So you can see plus 12 is connected to these two pins up here. Okay, it's connected to this pin here, pin 2 over there, that pin in here, and this pin down here. So it's actually connecting to many different places. Now, can anyone spot a problem with this pin 3 connection here? When you're looking at the plane that's associated with it. It's an island. Islands are usually suppressed if there's no pin connected to that island. But if there is a pin to that island, it's not going to get automatically suppressed. This is a suppressed island. That isn't. This would actually flag up on your net list, and there'd be a little green line telling you that's not connected. However, let's take pin 2. Can anyone spot what might be a bit of an issue with the connection that pin 2's got? If we've got high speed signals going through it. So, with high speed signals, immediate current draw, this trace meanders around, let's call it goes around the woods. It has to, you've forced the current in a way that it might not want to go. So, for example, you're going through that trace, that's blocked, can't get through there, can't get in here, comes around here, okay, then now it can connect to this. But what if you want that wants to, you know, connect to like this or even these over here? You'd have to go all the way around. Because if you think you can come through here, okay, you can get through that just about, squeezes through there, can't. So you might have created a lot of little thin traces connecting bits and pieces together on your circuit that you're not aware of. The only way to do this is to finish the design or be mindful of it as you're doing your design. You have to be mindful of it. What's the solution? So I moved that trace off that layer, and I actually used one of the internal layers. Another point is, actually, whilst we're here, on the internal layers, you want to keep them as solid as possible. So I've put a couple of traces on that layer, and these are the ground planes. And I've put one trace on there. i.e. I've not cut them up. I've kept them as solid as I possibly can. That's important part of good design, especially for EMC. So if we go back to here, so those traces that that are highlighted here that have disappeared are actually ones that are moved onto the inner layers at the end of the process. So now you can see that that pin 2 has got a solid, good connection to the rest of this stuff in here. Again, this is a power plane. It's less important for power planes to keep them completely uncut than it is the ground planes, because the ground planes contain all your return currents from the traces on the top and the bottom. But again, it's good practice. Right, so closing thoughts. Things to think about when you're doing design. The layer stack heights. Do you remember when we were setting up the layers in the PCB? Be cognizant that you've got 2 layers that are really close together and 2 layers that aren't. But the separation between the two is a lot. 6 layers plus is good for EMC. 4 layers is okay, 2 layers is bad, 1 layer ain't gonna work. We're not going to do much design for EMC yet, but I think that we should start to look at that. And as and when we start to test our circuits for EMC, you'll start to see these things that I'm showing you come into play, because you'll test the circuit and it'll fail, because I've done it. Placement is paramount. Untangle the roots before tracking. The placement of the components is one of the most important things you can do on a PCB. Get the placement right, and the tracking becomes a really enjoyable job. If you don't get the placement right, the tracking is a nightmare. Don't cut your ground planes up at all. Steadfast rule, don't cut your ground planes up at all. If you do cut your power planes up, fix them. Or you as a designer can determine that yes, that cut is okay, that device isn't withdrawing that much current. I'm happy with the inductance of that part of the plane for that component. And then this is an iterative process. You will put your components on, you realise that you hate it, you'll delete them, you put some tracks on, you delete it, and you'll forget that you put your volume potentiometer in the wrong place. It doesn't matter, it's iterative, especially for the first few that you do. So don't worry about redoing stuff over and over again to get it right. Cool, any questions?
How do you get
it doesn't. It stays. You need to make sure that what in the previous one I didn't show you, but when you turn the rat's nest layer on, there's a rat's nest green. There's a green rat's nest that will exist for that pin still, even though it's connected to that little island. The rat's nest is still there. So you will connect either the island to the correct plane, or you can connect the pin to the correct plane. But that island will stay there because there's a pin on it. If there isn't a pin on it, then the island gets automatically removed. Anything else? We good? Cool. Thank you for that. Okay, so the idea is again, it's a lot of work, especially if it's the first one that you've done. But for next week, I'm going to be showing how to get these things produced Gerber-wise, send them to JLC PCB, and how to put the bomb together, ready to be ordered. And then in the last week, if we get the boards in time, I'll hopefully demo a working circuit. So yeah, that'll be the plan. Cool. Thank you very much.